The other example we're going to do is question 23. Okay, so there's a representation of the diagram you've already got. We have essentially a trolley or a cart, and on that cart is a cylinder. Okay, trolley is connected to ground using this spring, and the cylinder is connected to the cart using this spring. And we've got x1 and x2, and the question says, write out the equation of motion in matrix form for the mass spring system shown in the figure. So, the way we're going to do this is we're going to do this using Lagrange's equation. And so, I have to find my kinetic energy and my potential energy. Well, T, kinetic energy, we've got translational motion, 1/2 m1 x1 dot squared. So that's the translational motion of the cart. Then we've got translational motion of the cylinder. But as the cylinder moves, it's also rotating, so we must also include 1/2 I omega squared. Now it's worth thinking about what omega is. We know that x dot is r times by omega, therefore omega is going to be x dot divided by r. That's the basic equation from level 1 dynamics. If you've got something circular that's moving along at velocity x dot with a radius r, then obviously it's going to rotate at omega. And the relationship between that and that is that equation there, or the tangential velocity at the rim. And so we can stick that into here. We know that I is going to be m2 r squared divided by 2. That's for a solid cylinder. And so we can rewrite this out, 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared plus 1/2 m r squared upon 2 x2 dot squared divided by r squared. This is m2, by the way. That's quite nice. My r squareds cancel. I've made a mistake. Obviously x2, we've got the relative displacement between these two here. So because obviously it's rolling on mass on the trolley, not on the ground. Okay, so it's not the x2 on its own, it's x2 minus x1. But those are dots and the whole thing's squared. So yeah, but like I said, because it's actually rolling on something else that's moving, then you have to use the relative velocities. Okay, and so the r squared terms cancel out. So here we go, x1 dot squared plus 1/2 m2 x2 dot squared plus 1/2 m2. We have x2 dot squared minus we've got 2 x1 dot x2 dot plus x1 dot squared. Oh, divided by 2 here. And then I'm going to group the terms together. So over here, we've got 1/2 m1 x1 dot squared, and we've got 1/2 m2 divided by 2 times by x1 dot squared. So I'm going to put 1/2 m1 plus m2 divided by 2 x1 dot squared. That's dealt with this term and this term. Then we've got, in terms of x2, we've got this one and this one. So I'm going to write out here 1/2. We've got 1 plus 1/2, so that's 3/2 m2 x2 dot squared. Oh, in fact, I'll put the bracket in there, just to make life easier. And then we've got, obviously, this term times by the one in the middle, so we've got 1/2 m2 divided by 2. Well, obviously, I've got a 2 in here, so just because that gets rid of this one, we've got 1/2 m2 x1 dot x2 dot minus. I'll write that out again just to be clear. Okay, 1/2 m1 plus m2 divided by 2 x1 dot squared plus 1/2 x2 dot squared minus 1/2 x1 dot x2. Okay, there's t. So that last line is exactly the same as the line above, but written out a bit clearer because I made a couple of mistakes. The potential energy is a bit easier. We've just got 2 springs. One is between the trolley and ground, okay, and one is between the 2 masses. And so V is 1/2 K1 x1 squared. That's between the trolley and the ground. And then we've got plus 1/2 K2. Because it's between the 2 masses, we have to talk about the relative displacements. So I'm going to write it like that. And obviously I could write this out. 1/2 K1 x1 squared plus 1/2 K2 x2 squared minus 2 x1 x2 plus x1 squared. And so again, I'm going to write it in common terms. 1/2 K1 plus K2 x1 squared plus 1/2 k2 x2 squared minus k2 x1 x2. So I'm going to now go down the Lagrange's route. That is t minus v. So this is just a matter of writing this term minus this term. 1/2 m1 plus m2 divided by 2 x1 dot squared plus 1/2 So I've just taken my t term and I've subtracted my v term to get this equation down here. Okay. Okay, so for x1, okay, you find the partial derivative of L with respect to x1 dot. Well, every term that's got an x1 dot in I need to deal with. So this one's a constant, this one's a constant, this one's a constant, this one's a constant. So it's only these two terms. Obviously, I take the derivative, I'll just get the 2 come down. 2 times a half is 1. So I simply have m1 plus m2 divided by 2 x1 dot. And then I've got this term minus 1/2 m2 x2 dot. Okay, the x1 is to the power of 1, so that just disappears. I take the time derivative of this. Well, basically, I have to take the time derivative of everything that varies with time. Well, x1 varies with time, and so does x2. So we have m1 plus m2 divided by 2 x1 dot double dot. Okay, minus 1/2 m2 x2 double dot. So now I take the derivative with respect to x without the dot on it. And so obviously all of those terms are constant. I've got this one and that's it. So it's just this term here. I have minus, the 1/2 disappears, k1 plus k2 x1, and I've got this term over here, plus k2 x2. So if I plug that into Lagrange's equation, I've got this term minus this term equals 0. So we have m1 plus m2 divided by 2 x1 double dot minus 1/2 m2 x2 double dot plus k1 plus k2 x1 minus k2 x2 equals 0. There's my equation of motion. So for the x2, I have to take all the terms with x2 dot in. So I ignore this one, I take this one, and I take this one. I ignore everything else. So I've got over here, I've got 3 over 2 m2 x2 dot minus 1/2 m2 x1 dot. Time derivative, exactly the same except for all the x's become x double dots. 1/2 m2 x1 double dot. Sorry? Yeah, it's okay. And then I have to take the partial derivative there with respect to x2. And so I've only got the terms with x2 in, which is this one and this one. So I've got minus 1/2 k2 x2. That disappears. So there's my second equation of motion. There's the first one. And there's my second one. Now the question says, write these in matrix form. Well, it just so happens that we can do so. So I've got mass matrix here. And obviously you have mass times acceleration, don't we? So x1 double dot, x2 double dot. And what goes in the matrix? Well, you can see quite clearly that we've got this term times by the x1 double dot, and this term times by x1 double dot. So we've got, over here, we've got m1 plus m2 over 2, and we have minus 1/2 m2. Here we've got minus 1/2 m2 as well. And over here we've got 3/2 m2. And then for the stiffnesses, you can see clearly from this equation we've got K1 plus K2 times x1 minus x2. So we have K1 plus K2 here, minus K2 here. And then here, with this one, we've got K2 times x2 minus K2 times x1. This is minus K2, this is K2. And that, it's unforced, so there is the solution in matrix form.